So let us start the class today. We have to cover the chapter Gravitation. It's a very small chapter. There is not much to know about this chapter, only a few points. If you keep in mind, you will be able to solve problems from any part of this chapter because problems are very important. Problems have been asked consistently every year in every exam possible. Chapter is important, but since it is short, you also require a lot of practice for this chapter in every type of question. Of course, let us revise the chapter quickly. Every important point we'll revise first, and then let's get on with the problems. The whole heart of this chapter is gravitational force. Gravitational force. And remember, the most basic form of this gravitational force is between two point objects m1 and m2. They exert a gravitational force on each other, and their value we know is given to be constant g into m1 into m2 upon the distance between them whole square. Hence it is also known as the inverse square law. These are both point masses. It is required to mention that both are point masses, right? But another important point that you should keep in mind is that the force on both the objects act along the line joining them. Of course, these are both point objects. I am drawing them of different sizes to make it visually clear that the masses are unequal. Of course, the bigger object will have a higher mass and the smaller object will have a lower mass. But these are point object, and the line joining them is the line along which all forces act, especially gravitational force. Right? From this diagram, this thing should be clear. And if we have extended objects, let me take it up. If we have extended objects, let's say this is an extended object and we have one point object, the mass of this bigger object is capital M and the mass of this smaller object is small m. In that case, since we already have a law for point objects, what we can do is we can consider a small mass element of mass dm on the extended object and draw a position vector to the point mass from that mass element. Right now, this position vector depends on which particular mass element we are choosing on the extended object. So of course, the position vector also carries information about the geometry of this extended object, and hence the force between them dF will be given as constant g into m into mass element dm upon position square. If we integrate this all over the entire mass m, then we will have the force between the two objects. Right? I hope all of you remember this much. If you just know the inverse square law and how gravitational force acts, the chapter will be very straightforward for you, because everything that we are doing in this chapter is based on this one statement. Now, if the geometry of the object is some complicated thing, then the statement for the integral will also become complicated, right? Integral will be very difficult to solve. There are some integrals that simply cannot be solved by hand. We call them non-analytic integrals. They cannot be solved by hand. They can only be solved numerically. Of course, those type of integrals are not technically in your syllabus, but just know that some complicated integrals we simply cannot solve by hand. So we need some way to get around this fact. If we have a object which has some symmetry, then we can exploit this. That is, we can say Okay, since the point mass m is at some distance from the object and the gravitational force between them depends on the square of this distance, right? So if we keep the distance between the point mass and the extended mass constant and move the mass around, for example, if we move this point mass somewhere over here, keeping the distance constant, then we can see that the gravitational force on it will also be constant. For example, if we move it all the way over here also, since the distance is same between the two objects, the gravitational force also has to be same, right? So here we can guess that the gravitational force is depending on the position of the small point mass if the bigger extended object is kept constant. We can exploit this fact to say that, okay, imagine that there is no extended object over here, but there is some property all over the space. That property exerts a force on this mass, point mass, based on its position, right? Why does that work? Because we know that there is a mass over here and that mass is exerting a force depending on the position. But since this mass is very complicated to calculate, we can imagine that there is no mass and there is some imaginary quantity everywhere in space that is exerting force. We call that imaginary quantity as field, also gravitational field, we say, and that quantity we denote by the symbol E. And what does it mean? It means that based on where this object exists in space, this quantity, gravitational field, will exert a force on it. It exerts a position dependent force. And of course, the force will also depend on the mass of this point object, right? So we know that this gravitational field will exert a force on the object depending on where it exists in space, and it will also be dependent on its mass. So we can define the gravitational field as force per unit mass to make it independent of any point object. Force per unit mass becomes the definition of this gravitational field quantity. First of all, the motivation for defining a gravitational field in this way is that we need to simplify our calculations, right? Most of the quantities in physics are motivated by the same fact that we need to simplify our calculations. So we define a quantity that is easier to calculate, simple. And this quantity is independent of the object on which it is exerting force. That is, even if we simply have an extended object of mass capital M, we know that if any object comes into its vicinity around the extended object, obviously, then there will be some gravitational force acting on it, and that gravitational force will depend on the position of this object and on the mass of this object also. So we can define this quantity field as the force that this extended object should exert on any unit mass point object. So if any object enters its field, then we can simply multiply its mass and exactly calculate how much force is getting acted on it, right? Simple. The total gravitational force getting acted, of course depending on position, will simply be equal to the mass of the object into the gravitational field due to the point, so extended mass m at that particular point, right? The definition of gravitational field is force per unit mass. Is this clear or not? Quickly tell me. And for this kind of extended object, we can write the gravitational field as simply G into dm by r square and integrate it. This is also defined as the acceleration due to gravity at that particular point. Acceleration due to gravity is simply gm by r square, the gravitational field at that point. Why? Because this is basically acceleration. Force per unit mass is simply acceleration. If we consider any point object or any object at some distance from it, the acceleration that that object will experience at that point will simply be the value of the gravitational field at that particular point, right? It's simple, right? And of course direction, we can see that it will be towards the extended object. So if we provide a direction vector as the position vector itself, then it will be away from the position vector. If this is the point and this is the position vector r, then the gravitational force will act opposite to its position vector. Hence, to denote the opposite direction, we use a negative sign with the unit vector for the position, right? Should we take an example of gravitational field calculation? Let's take a very standard example. Let's say you have a uniform ring kept in the horizontal plane. This is the horizontal plane and you have a uniform ring kept over here. Let me write it as uniform ring which has a mass of m and radius of r, capital R. Radius is given to you. Consider a point along the axis of a ring, that is a line passing through its center. This is the center, right? Yes. Consider a line passing through its center and perpendicular to the plane of the ring. This is what we call axis, right? If a point exists on the axis at a distance of z from the center, what will be the gravitational field at this point? Very standard example. All of you should be able to do this. Tell me, what will be the gravitational field at that particular point along the axis? It shouldn't take you more than 2 minutes. So think about it, do all the calculations, and then I will start giving you spoilers. GMZ upon, yes, most of you might remember this formula. If you have done this derivation yourself, then you will definitely remember it. As I said, if you want to remember any formula, all you need to do is derive it by your own hand. You will never forget it in your lifetime, even if you try to forget it. Just derive it once and you will remember it forever. Yes, I can see some correct answers in the chat. Some of you might have derived it right now. Some of you might remember it. Both are very good cases. If you are driving it right now, then you will probably never forget it. Gravitation and exactly the same. Yes, exactly. You're right. Let us see. We know that we need to consider some mass element dm on it, and the gravitational force will be along the line joining these two masses. So the gravitational field should also be along the line joining these masses. right? Let us consider the top view of the ring. Let us consider the ring as we see from the top. Mass is m, radius is r. And let us consider a mass element dm of thickness. Okay, let's say mass element dm, we don't require thickness right now. We know that this mass element dm will exert a force. Okay, I think if the mass element is over here, let us draw the mass element at the extreme point for easier visualization. This is the mass element dm at the extreme point, and it will exert a force in the direction joining the 2 points. So if we draw a force on this point, there will be one force df or gravitational field dE along this direction, right? But if we consider a diametrically opposite mass element, and let us write it in, okay, let us write the top element in blue, dm, so that the mass element at the diametrically opposite position will exert a same value of force but along the opposite direction, right? A mass element dm over here will exert a force along this direction. One force will be along this direction and one force will be along this direction. Both of them will have the same magnitude dE, but since their horizontal components are opposite to each other, their horizontal components will cancel out. Is everyone able to see that horizontal components both cancel out in this case, and their vertical components get added up? It's easy to see, right? The vertical components will get added up. And what will be the vertical component of both of these vectors? Tell me quickly tell me what will be the vertical component value. The radius of the circle is given to be r and the height is given to be z. So the distance between the point and every single mass element dm will simply be the hypotenuse of this triangle. Hypotenuse will be under root r square plus z square, right? Simple Pythagoras theorem. And the angle that this hypotenuse will make with the vertical theta will just be sine inverse of r by hypotenuse or cos inverse of z by hypotenuse, right? Since the angle the direction makes with the vertical is theta, this angle will also be theta. And the vertical components are nothing but the cos component of dE. The vertical components get added up from here. Vertical components add up. So all we need to do is add all the vertical components of gravitational field dE due to a mass dm, right? Let us do that. The total gravitational field will be, okay, let's just calculate the value. We know the gravitational field will be along the z direction. Gravitational field will be g into dm upon r square is simply the hypotenuse square, r square plus z square, and cos theta will simply be z upon under root of r square plus z square. And if we integrate all over the mass, we will get the total gravitational field. Similar to MEEC Biot-Savart law. Okay, that is in the magnetism chapter. Let's not get into that now. This is how we'll get the gravitation field. Now Z is a constant, G is a constant, radius, everything is a constant. So all of these values will come out of the integral, and the only thing remaining inside the integral will be dm. If we integrate dm, we will simply be left with the total mass of the object. So the net gravitational field becomes G into capital M into the height Z upon r square plus z square raised to 3 by 2, because we are multiplying r square plus z square and under root of r square plus z square. This is how we calculate the gravitational field. And of course, its direction will be along the positive z direction, we know. Is it clear? The only way to make mistake over here is to forget that horizontal components also get cancelled and only vertical components get added up. That is the only mistake you can make over here. There is no complicated integral over here. All of the points dm are equidistant from this point. But if in case you get an example in which the points are not equidistant, then the denominator r square plus z square, if z is a variable, that will get integrated along with dm, right? Yes, exactly. Once we do electrostatics, you will see that electric field also behaves exactly the same. But there is a fundamental difference between the electric field and gravitational field. That is, electric charge can either be positive or negative, whereas gravitational mass can only be positive. If electric charge is negative, then the force or the field is of attractive nature, and if the electric charge is positive, it is of repulsive nature. Gravitational force is always of attractive nature. Gravitational force cannot repel any object. Clear? This is the fundamental difference between gravitational force and electrostatic force. Gravitational force cannot be repulsive, it is only attractive in nature. Is this clear? Can we move on? Can negative masses exist? Negative masses cannot exist, but we can imagine a negative mass for simplicity. That is, what if we have a disc, a circular disc, but we drill a hole inside the disc? As such, only this is the mass of the disc that is exerting gravitational field. If we know the gravitational field due to a uniform disc, and we are supposed to find the gravitational field due to such a configuration, that is a disc with mass removed. Let me write over here, a disc with some portion removed. In this case, we can imagine that this system is made up of a uniform disc, and we are adding a small disc of negative mass disc we are adding. And since we know the gravitational field due to a uniform disc, we know the gravitational field due to the entire disc without the removed object, and we also know the gravitational field due to this small disc, but its mass is negative. So we can add both the gravitational field considering the negative mass and then find the field due to the entire object. Even though negative masses don't exist in reality, we can imagine a negative mass. Its physical significance is that the mass has been removed from the entire object. Is this clear? Should we move on? If anyone wants to ask anything else, please ask in chat. but slowly and steadily. Please don't spam, otherwise I won't be able to read your doubts. Anyone wants to ask anything till gravitation field? The next concept is also pretty obvious. Can we say gravitational acceleration arises tendency of object to reduce its state of energy? Yes, exactly. You are right. In fact, any motion arises because it wants to reduce its energy, right? Direction of electric field should be that the force experienced by an object, if it is present there, so shouldn't the force be in the negative z direction, as the force is attractive. Oh yes. Sorry, my bad. The force will be in the negative z direction. Yes, we had included a negative sign over here. I completely forgot about that. My bad. It should be in the negative z direction. Let me also invert this diagram. Thank you so much for pointing it out. It should be in the negative z direction. Yeah, this is fine now. The force experienced by the negative mass, it will be attractive in nature. Yes, exactly. Should we move on now? Just like we defined this quantity gravitational field that exerts a force on any object in the vicinity of this mass, right? And we know that once an object starts experiencing some force, it will start moving. And since the object is moving under the action of a force, the force will also do some work and the object will gain some energy from the gravitational force. We define that as the gravitational potential energy. Potential energy. Again, remember the chapter work, power, energy. If any conservative force is acting on an object, there is an associated potential energy, right? Gravitational force is position dependent force, right? That is the definition of a conservative force. So gravitational force is conservative in nature, hence we can define the gravitational potential energy also in the same way as integral of F dot dr. Right, this was the definition of potential energy from work, power, energy chapter, and the same definition holds for gravitational force also, since it is a conservative force. It is dependent only on the position of the object. And accordingly, to simplify our calculations, we can consider another quantity that exists everywhere in space, but instead of applying a force on the object, it imparts some energy on the object. That is, if we have any extended object, we know that any object in its vicinity will have some potential energy because of the gravitational interaction, right? So we can do the same treatment. Imagine there is no object here, but there is a quantity everywhere in space that gives some energy to the object dependent on its position. So in a way, this is also a field, but we call it as gravitational potential. Gravitational potential. As you study higher physics in IISER, you will learn that the word field is a very general term. You will learn this, I guess, in your third year of IISER. If you decide to pursue physics after 12th, then you will learn that the word field is a very general term, and it means any quantity that is position dependent. So let us say if there is a space, that is everywhere in space there is a quantity such that if I keep an object over here in that space, that quantity gives the object some mass. That is, just by existing somewhere inside that space, I am gaining a mass because of that quantity, depending on, of course, where I am existing. That is called as a mass field. Why? Because it is providing mass to any object kept inside of it. Similarly, any field that exerts a force depending on position is called as force field, and any field that imparts energy to an object will be called as energy field. You will learn all of this as you pursue higher physics, but I am just telling it to you now just so that you have some simplicity in understanding the concept of field and everything. Yes, Higgs field you must have heard, that's also the same thing. Is there theoretical physics in IISER? Obviously, I have studied theoretical physics in IISER, so there must be. Again, let us keep all these doubts for later. Let us continue with our chapter now. Gravitational potential, we define similarly to gravitational field as the potential energy per unit mass. Potential energy per unit mass, that is, any object kept inside this quantity will experience some potential energy depending on the position and on the mass of the object. And we define it to be the same way, that is, potential energy U will be equal to mass times the gravitational potential at that point. The symbol is V, and since we define potential energy as minus of integral of force, if we just cancel mass from the force, we get the definition of potential, that is minus of integral gravitational field into dr. We get the definition of potential, right? Even this is very simple to you. Can we take the same example again? That is, can we now find the gravitational potential due to some uniform ring at a point on its axis? Mass is m, radius is r. Let us make an axis at a distance of z. What will be the gravitational potential? Can you guys find out? Why negative? That is the definition of potential energy. Remember, in work power energy, we had defined the potential energy as the amount of work done that is required by a force to bring an object from infinity to some particular point. That is, if I have a point mass m kept at infinity. Infinity simply means at a very large distance from the ring. So, if the distance between the object and the ring is some d, which is much larger than the radius of this ring, then we can say that this mass is at infinity. That is, gravitational force acting between them is almost zero. It is very negligible. If I want to take this object from infinity and put it at this particular point, then the work done by the gravitational force should be equal to the potential energy at that point. Clear? Which is why we have a negative sign, because work done at any point is simply integral of force. To get a point from infinity where there is zero energy to some particular point will give a negative sign. There must be r instead of z in the first question answer. R instead of z over here. No. Cos theta will give us r only. The angle is with the vertical, right? The vertical component should have the vertical cos theta component. Cos theta is z upon r square plus z square under root. So yes, there will be z over here, there will not be r over here. Now since we know the gravitational field due to this ring already, we have calculated it already. So gravitational potential we can just write as integral of gravitational field to dz, right? We can simply integrate the gravitational field and write its potential. You can do the long way also. You can again assume a mass dm, then find the distance between them, find the potential due to this point mass, and then integrate all over the ring. You can do that also. It will be the same integral as before, but instead of cos component there will only be r square plus z square. You can do that, but let us do this because this is even tougher. We need to integrate negative sign from here and negative sign from here will get cancelled. All we have left is z upon r square plus z square raised to 3 by 2. So gm into integral of z with dz upon r square plus z square raised to 3 by 2. How will you integrate? You will substitute some u equal to z square. The substitution you require is u equal to z square. Then du will be equal to twice of z into dz. We have z into dz over here. So z into dz becomes simply du by 2. We can take that half out of the integral, right? So the integral becomes gm by 2 into integral of du upon u was z square, so r square plus u we get. But we can go one step further and define u to be r square plus z square itself. Since r is a constant, du will not be affected at all. So we'll just be left with u raised to 3 by 2 and integral du, right? And you know this integral is simply x raised to m integral, and integrating we get x as gm by 2 into m plus 1, that is minus of half. So minus of 2 upon u raised to half will be the integral, right? 2 and 2 will get cancelled and the final value of potential will come as minus of gm upon r square plus z square raised to half. Yes, minus of gm upon root over r square plus z square. Can you explain how that in ring the 2 dE cos theta integral, the integral is not 2 dE cos theta over here. It is not 2 dE cos theta. Since we are adding up the vertical components only, the integral is simply dE cos theta is the required electric field. And since this is a triangle, this is the angle theta, cos theta is adjacent side z upon the hypotenuse, right? So integral dE into z upon under root of r square plus z square. This was just a demonstration that the vertical components get added up and the horizontal components get cancelled. If we are only calculating the gravitational field due to these two objects, then yes, it will be 2 dE cos theta. But if we add a point mass over here, it will be 3 dE cos theta. Similarly, adding all the point masses, we are adding dE cos theta everywhere. 1 dE cos theta from here, 1 dE cos theta from here, 1 from here, 1 from here, everywhere we are simply adding dE cos theta. And we get the electric field, sorry, gravitational field. I keep saying electric field. Since we have the gravitational field, we can simply integrate it to get the gravitational potential also. The gravitational field depends on Z, so integrating it with respect to Z should also be easy. You know that there is Z square in the denominator and Z into dZ in the numerator, right? So we can substitute such that Z into dZ should come out to be simply du as part of the substitution. We can take the entire denominator r square plus z square to be a substituted variable u, and from here du will be equal to twice of z into dz. So we can multiply and divide by 2 over here, that will give us gm by 2 into du upon u raised to 3 by 2, as r square plus z square has a power of 3 by 2 in the denominator. Now there are some other topics that you need to keep in mind, and if you derive them once by yourself, you will never forget it ever in your life. We don't have enough time to go over all of those derivations by ourselves, but just the results, let's take a look. The major application for gravitation immediately for us is the earth system, right? This is the earth. If we are sitting at some point over here such that the latitude at that point is given to be lambda. Lambda is called the latitude, that is, it is the angle made by the horizontal at that particular point. The earth is rotating with some constant angular velocity omega, right? And because of that, this is called the effect of rotation. The acceleration due to gravity at this particular point gets reduced. The acceleration due to gravity at some latitude lambda is equal to the acceleration at the surface of equator minus of omega square into r into cos square lambda. This is how the acceleration due to gravity varies due to rotation of the earth. Yes, exactly, it is because of the centripetal force. Some amount of weight of the object has to provide enough centripetal force to keep the object moving in a circular path along with the earth, right? Some weight of the object goes into providing centripetal force. This is the centripetal force required, the centripetal acceleration required along the weight. Some amount of the weight goes into providing centripetal force and remaining is observed as acceleration due to gravity. Clear or not? So if the earth was rotating at a very high angular velocity, then we would experience weightlessness at the poles. So not at the poles, at the equator. We would experience weightlessness at the equator if the earth was rotating with a very high angular speed. But the angular speed of the earth is limited. We know the time period of the rotation of the earth is 24 hours. That is the duration of a day. And time period is simply 2 pi by omega. It should be 24 hours. This is how we calculate the angular speed of rotation of the earth, 2 pi upon 24 hours. And the acceleration due to gravity also varies if we exist at some height h above the earth. Of course, we know that the acceleration due to gravity at height h will simply be gm upon r plus h. the whole square, right? The acceleration due to gravity is simply the gravitational field at that particular point. But we need to express this in terms of acceleration due to gravity at the surface. Let the acceleration due to gravity at the surface be g, we know. And what is g? G is simply gm by radius of the earth square. So if we want to calculate this in terms of g, we can multiply and divide by r square. What will happen because of that? Why is it necessary? So that we can divide this r square with our gm. This r square we can divide with our gm and write it as gm upon r square, and then we have r square upon r square plus h square over here, sorry, r plus h the whole square. This is how we can rewrite our acceleration due to gravity, right? Now we can rewrite r plus h the whole square as, we can invert this r plus h upon r, and we can have a negative power in the numerator. It's the same thing, right? And we can take r outside, distributed 1 plus h upon r will be left to us, and gm by r square is simply the acceleration at the surface g. This is how acceleration due to gravity varies with the height. We multiply and divide by r to make gm by r square as acceleration due to gravity g. You can see gm by r square is the acceleration due to gravity at the surface. We want to express every point in terms of the value at the surface, just like we did for rotation. This is known as effect of height. Effect of height. And of course, even satellites orbiting the earth will experience this gravitation acceleration. Yeah. And by using some laws of motion and some work power energy, you can also calculate some properties of satellites, as let's say you have the earth over here and some satellite that is orbiting at a height of h as usual. Then of course we don't have time to go over the derivations, but you need to know the values. The satellite will be orbiting at some velocity. We call it the orbital velocity of the satellite. Orbital velocity is defined as v for a height h will be equal to under root gm upon r plus h. This is the velocity with which satellites orbit. Of course, you can calculate the gravitational force due to earth and equate it to the required centripetal force, and you will get the orbital speed, right? And from here you can calculate the time period of the satellite also. Time period will be the time taken to complete one particular circle, that is 2 pi r, radius of the orbit will be r plus h, upon the orbital speed vh will be the time period of the satellite, that is the time required by the satellite to cover one full circle. Yes. And substituting the value of vh we get the time period as 2 pi into r plus h upon under root gm into r plus h, right? So 2 pi into under root of gm upon r plus h the whole cube, because we are multiplying r plus h along with r plus h ka square root also, right? And since time period is 2 pi by omega, the angular velocity of rotation will be gm upon r plus h the whole cube. From here the concept of geostationary satellites or geosynchronous satellites arises, that if a satellite has the same time period as the rotation of the earth, then this satellite is said to be geosynchronous satellite, right? Of course, only the definition is required. You don't need to know exactly what height the geosynchronous satellite will be and all of those things. So consider that there is a geostationary satellite that is orbiting the earth at some height of h. The mass of the earth is m, radius of the earth is r, the height of geostationary satellite is h. Now if the radius of the earth shrinks to half of its size, half, that is suddenly the radius of the earth becomes half, the earth shrinks suddenly, then what should be the new height of a geostationary satellite? Question is clear? You know that if radius of the earth is r, then height of the geostationary satellite is h. You've been given. If the radius of the earth shrinks by half suddenly, then what should be the new height at which the satellite will be geostationary on this earth? We use conservation of angular momentum. You can use whatever tools you want. Geostationary time period is simply 24 hours. Look at how the question is phrased. The question is phrased, what will be the new height above the surface of the earth? We know what will be the speed of the satellite at some point, right? By conserving centripetal force, we have calculated the speed. So initial speed of the satellite was V initial is equal to gm upon initial radius plus initial height under root, and if the radius shrinks by a half, then final speed will be gm upon this half radius r by 2 plus the new height h dash, right? H dash is the height after the radius shrinks from the surface, and since the radius has shrunk to half, the total radius of the orbit will be r by 2 plus h dash. Now in all of this, radius shrinking, height changing, since the satellite is in a geostationary orbit, through and through, we should conserve energy. The energy should be conserved of the satellite before the earth shrinks and after the earth shrinks also. That is the kinetic energy before shrinking of satellite and kinetic energy after shrinking of satellite should be the same, right? Technically, kinetic energy and potential energy both adding up should be the same. Velocity staying the same is not the condition. Why? Because as the earth shrinks, the rotation of the earth might also get affected. So we cannot say that for the satellite to remain in a geostationary orbit, the speed should remain unchanged. No, we cannot say that. Why? Because the angular speed of rotation should also technically change. It may or may not change, yes, but technically the angular speed of rotation can change if the earth shrinks, right? So, but the energy should remain constant. Let us conserve energy. Half into m into vi square plus gm, sorry, minus of gm, potential energy is negative, upon r plus h should be equal to half into m into v final square minus of gm upon r by 2 plus h dash. This is how we conserve energy, kinetic energy as well as potential energy. Remember, gravitational potential energy is always negative for a mass. If we substitute the value for initial and final velocities, Vi is gm upon r plus h. Gm upon r plus h, we will substitute over here. Bring this term to the other side, and Vf is again gm upon r by 2 plus h dash. Right, there will be a small m also over here. So all of the terms combined have to be equal. We have g into m upon r plus h, and we have g into m upon half of r plus h over here. So our energy conservation simply becomes minus of g capital M into small m upon r plus h should be equal to minus of g into capital M into small m upon half r plus h dash. That is, the radius of the orbit of satellite should remain unchanged. R plus h should be equal to r by 2 plus h dash. So the new height h dash will simply be the radius after shrinking plus the original height. Because of energy conservation, the radius of the orbit, the total radius of the orbit should remain unchanged. Hence the height will be the remaining radius, that is half the radius plus the original height. You can conserve angular momentum also, but then you will have to conserve the angular momentum of the earth as well as the satellite. Both of the angular momentum you have to conserve if you are going by that route, but that's a much tougher thing to do. The most obvious is energy conservation. Clear or not? Clear or not? Tell me. We found the orbital velocities and then conserve energy, but the change is r by 2. Now, why both are same? What do you mean both are same? The initial radius is r plus h. The final radius is the shrunk radius plus the new height. You can simply answer by intuition. Radius is half. Again, if by energy conservation you can see that radius of the orbit should remain unchanged, because the total energy of the orbit only depends on the radius of the orbit. So orbital radius should remain unchanged. Then you can easily guess that the height will be the remaining part of the radius plus any original height we had. Then all that is left now is Kepler's laws. Kepler's laws is honestly not an important topic for IAT and NEST. Kepler's, because they are mostly calculative in nature. Kepler's laws are important from the point of view of JEE, but they are not important in IAT or NEST. The first Kepler's law is that planets orbit stars in elliptical orbits. That is, the orbits of planets are not circular, they are an ellipse. So using all the properties of ellipse, you can also get all the properties of planetary orbits. You need to know the properties of ellipse from coordinate geometry in maths for this. Second law of Kepler is that if, let's say, this is the orbit of a planet, this is the star along one of its focus, and a planet is orbiting such that it covers this much area in time t, and let's say this area in the same time t. Kepler's second law says that both of these areas will be equal if they both take the same time. We call this the area swept by the planet in this particular time. Kepler's second law says that the area swept by a planet in equal amounts of time is equal if the star is, of course, at the focus. The alternate statement is that angular momentum is conserved. Angular momentum is conserved. Derivation is not important, obviously, but if you guys want the derivation, then I can send you the notes separately, but you don't need to know the derivation. All you need to know is that area swept is equal and angular momentum is conserved for a planetary orbits. They both are the same statement. That is, you can derive one statement from the other statement. And third, Kepler's law says that the time period of orbiting of a planet around the star goes as the cube of the radius. That is the average distance between the planet and the star in the ellipse. We call that as the planetary radius, right? And the exact statement is that time period is equal to 4 pi square upon gm under root into r raised to 3 by 2. This is the exact value of time period from the radius. Of course, you can calculate this by conserving centripetal force. We have already seen time period raised to 3 by 2 we get from here, right? We have already calculated that time period as the radius, and we know that it goes at radius raised to 3 by 2. Let us take a question on this fact also. Let us say that the earth is moving around the sun. The mass of the sun is, let's say, capital M, and since the earth is moving around an ellipse, there will be a closest approach to the sun and a farthest approach from the sun. That is, there will be a point where the earth is the closest to the sun. We call this point as the perihelion. Perihelion is the closest approach. Closest approach is given to be r1. The earth has a perihelion distance of r1, it is given to you, and the distance of the farthest approach is known as aphelion. That is the farthest approach. is given to you as r2. You need to calculate what will be the angular momentum of the earth in terms of only m, r1 and r2. All you've been given is that the mass of the sun is m, the closest approach to the earth is r1, the farthest approach to the sun is r2. You need to calculate what will be the angular momentum of the earth. We have been given the closest approach and the farthest approach, right? Orbit is this way. Since we know angular momentum is conserved, when the earth is at the closest approach, the gravitational force should be the highest, that is centripetal force should be the highest, and the velocity should also be highest. Centripetal force at the farthest approach should be the lowest and the velocity should be also lowest. Is everyone able to see this much? That in the farthest approach velocity should be higher, and at the farthest approach velocity should be lower, and at the closest approach velocity should be higher because of centripetal force. So let us first conserve linear momentum over here. Let us say that at the perihelion the velocity was v1 and at aphelion velocity is v2. So conserving momentum, we get m into v1 should be equal to m into v2, right? v2 is simply they both should be same. No, angular momentum is conserved. Angular momentum is conserved, not the linear momentum. M into V into R should be equal to M into V2 into R2. Angular momentum is conserved according to Kepler's law, right? We are conserving angular momentum, mass will get cancelled, and velocity at aphelion will be equal to velocity at perihelion into R1 upon R2, that is the ratio of perihelion upon aphelion, right? Everyone understood this? Simply by conserving angular momentum according to Kepler's second law, we get the relation between the velocities of aphelion and perihelion. This was velocity conservation, angular momentum conservation, but we also need to conserve the energy, because energy in an orbit should also be conserved. Energy is conserved always. In a planetary motion, angular momentum is conserved according to Kepler's law, but energy will always be conserved. Just like in a collision, we had conserved momentum for when external forces are 0, but energy was conserved always. So let us conserve energy between the aphelion position and the perihelion position. At the perihelion, we now know the velocity as v1. So kinetic energy will be half into m into v1 square. Potential energy will be minus of gm into small m upon the perihelion distance, that is r1. Similarly, at aphelion, kinetic energy is half into m into v2 square. Potential energy is gm into mass upon the aphelion distance r2. Is this fine to everyone? We are simply conserving energy over here. Now if we substitute the value of the aphelion velocity over here, we can write v2 square as v1 into r1 upon r2 square. So v1 square into r1 square upon r2 square we can write as the aphelion velocity in the energy statement, right? Now m will get cancelled from all the sides as usual. M, everywhere we cancel m, and we need to calculate the angular momentum in terms of r1 and r2, right? Let us take all the gm terms on one side and all the velocity terms on the other side. we take Gm upon R2 to the LHS. So Gm we can take common from both of them, and we have 1 upon R2 minus 1 upon R1. Right? We take all the Gm terms on the LHS. We know 1 upon R2 minus 1 upon R1. If we cross multiply, we get R1 minus R2 upon R1 into R2. Right? And on the RHS, similarly, we get half m into V2 square. Sorry, this is V1 square, right? Half into m into V1 square. M is cancelled, so we can simply write half into V1 square and R1 square upon R2 square minus of 1. And if we take the common denominator, we will get R1 square minus R2 square upon R2 ka square. Now look at this term, R1 square minus R2 square. Can we write it as A plus B into A minus B? Right? We can write R1 square minus R2 square as R1 plus R2 into R1 minus R2. So R1 minus R2 will get cancelled with this, and what we will be left with is simply R1 plus R2. And of course R2 will get cancelled with R2 square, and this bracket becomes R1 plus R2 into R1 minus R2. R1 minus R2, R1 minus R2 gets cancelled from here as well. So we get the value V1 as 2Gm will be in the denominator. V1 is equal to twice of Gm. The 2 will go on the numerator on the other side, and this R2 will also go in the numerator. So 2Gm into R2, and in the denominator we will be left with R1 plus R2 into R1. So R1 into R1 plus R2 will be left in the denominator. The square root will give us the value of V1. Is everyone fine till here? How we got the value of V1 from here? By conserving energy and doing some manipulation to the equation, you will get the value of R1. Now the angular momentum, let me draw a boundary over here and also a boundary over here. Angular momentum is L is equal to m into V1 into R1, right? Since you are multiplying V1 and R1, the R1 in the numerator will get cancelled and it will come in the numerator inside the square root. So angular momentum will be m into, substitute the value of V1 twice of G into m R1 R2 upon R1 plus R2. This will be the value of angular momentum. R1 was outside V1, so we multiplied R1 square inside the square root and cancelled with the denominator. That's how we got R1 and R2 in the numerator. Again, this was a next level question because it is a very lengthy calculation. But since this is a symbolic question, once you understand what you need to use, conserving angular momentum and then conserving energy, you will not make a mistake. If you make a mistake, then it will be obvious to you if you look at the steps itself. Right? Keep in mind that energy is conserved always. In every single system, energy will be conserved. Linear momentum will be conserved if there is no external force, and angular momentum will be conserved for a planetary orbit. So just by conserving angular momentum and energy, you will get the answer. Just like when we did collisions, we conserved linear momentum and the energy. But over here we conserve angular momentum and the energy. Question is simple, but the calculation is lengthy. This is what makes it a next question. All right, fine. This was the chapter Gravitation. Let's wrap this class up today. And in the next chapter, I guess we can start with 12th standard syllabus from electrostatics. See you all in next class at the same time.